last week we talked about the unstable amplifier put into such kind of negative feedback application to make it stable. And we also mentioned this. In the past, we only design stable op-amp with stable application, but finally, we help you to expand your territory into the other new place. Here, you can see for the op-amp, actually the power, the dominant power actually is to the right. So it is unstable. But before this, the overall application is still stable. So here is the new territory for you. With stable, with unstable op-amp, we can still achieve stable application circuits through negative feedback. Yeah, so in the past, we apply negative feedbacks for 2 times. First of all, for op-amp design, and then for your negative feedback application. It doesn't make any sense, right? So here, usually we hope you can design with positive feedback for op-amp to enhance the gain, and then apply negative feedback to make the overall application stable. That is the logic thinking, yeah. And this is never happened in the past. And I also told you, yeah, a little bit, if you design the dominant power of the op-amp a little bit to the right, a little bit unstable, actually, it can not only enhance your gain, but also it can reduce the settling time. Okay? That is a very important idea for you to follow. But you may be curious, what kind of positive feedback, because in the past you only focus very much on negative feedback, but what kind of positive feedback you can apply to enhance your gain for op-amp? First of all, you can see this. Yeah, such kind of close connection. Yeah. In theory, if you apply your small signal analysis here, you can see actually it is some kind of negative impedance. And what we would like to get is use such kind of negative resistance, impedance to cancel the other positive one. Okay? For what? To make infinite resistance or zero conductance, zero output conductance. That is what we would like to have. Okay, anyway, anyhow, yeah, this is what you can do. If you are interested in derivation analysis, go for it. After some time, maybe tens of minutes, oh, you get this. Very good. What we would like to say is, if this one, GM4 means the transconductance of this and that, okay? Then, if we can make them exactly the same, the positive term and the negative term the same, congratulations, this will be 0. So for DC again, DC means no this, right? Because S means J omega 2 pi F, right? 0 frequency means 0 here, 0 there. Congratulations, you get infinite gain. That is in idea, okay? That is idea, but how about the reality? The reality is, we tell you again and again, you can only match the same parameters, not only the same device. Even for the same device, you cannot say, hey, I would like to match the gate to the source or to the drain. No. It doesn't make any sense. Only when those are fabricated, produced at the same time, they can be matched to each other. So usually the same layer, the same parameters. So you can see the transconductance cannot match. It can be matched to this, but it cannot match It cannot be matched to the others. Sorry for that. Okay? Maybe we say, hey, look, during design, I try my very best to make this cancel all of them. Yes, that is only in theory. But in practice, after fabrication, yeah, everything will go wrong. You cannot match this to all of them. That is really upset. Yeah, maybe the problem is here. You cannot match this to GO type. GM cannot be used to match G out. Okay? Now what we can do is, okay, if you cannot make it, then maybe from the previous one you can see it connected in this way, diode connected, right? Then we try to have some kind of bias voltage for tuning. Yeah. Anyway, anyhow, during design you can match anything, but after fabrication, sorry for that. What you can do? We have something to be tunable. Yeah. Then try to tune the G out of this one and that one to be matched to the others. Blah blah blah. Okay. Anyway, anyhow. Yeah. After derivation, yes, you get the same thing, but you can see that this and that are tunable, right? So after fabrication, even though this and that cannot be matched exactly, but you can tune this one and that one to make it 0. Yeah, if you have some kind of measurement, calibration, okay, if you have some kind of calibration or trimming, then you can do it to enhance the gain. Yeah, but that is only the idea. So let's go further for some kind of sample design implemented by Professor Geiger and his students. So he would like to show you 3 new positive feedback amplifiers. Yeah, from the very beginning, negative conductance or negative impedance amplifiers you like, or positive feedback or GM attenuated amplifier. Yeah. So, for example, this is the so-called negative G out compensation. Yeah. What is the logic thinking behind such kind of circuit? Again, if you go back, never mind how hard you try, you can see GM cannot be used to match G out, right? You can only match GO to the other GOs, or you can only match GM to the other GMs, but nothing in between. Okay? So you cannot compare apple to orange. Yeah, you can only compare apple to apple, orange to orange. That is the same idea. So hopefully this is the original logic thinking. Yeah, GR1, GO1, GO2, and GO3. They can cancel each other, right? So GO, or how can I say, or RO, as you like. RO1, RO2, and this is RO3, right? So you need to make, because RO1 and RO2, they are regular, they are from regular transistor, so they are all positive. You need to make this negative. That is the logic thinking. Okay, the same R out. R out is measured from source to from drain to source, right? That's it. And so here also from the drain to source here to there. Anyway. So if you see, this is if you increase it, it means what? According to AC, the AC current from this node will also be increased. Okay, because you have RO1 in parallel with RO2. So if you increase this, the current will also be increased. Okay, yeah. And you can see that for this one, if you increase V out, so the output will also be increased substantially. So what does it mean? The VDS will be decreased very much. So it means what? Because from the beginning, you can see it conducts some current, right? And then if you increase it, then, as I mentioned, this will increase substantially. So the current here will be decreased substantially. So what does it mean? Some kind of AC current flows out instead of flows in. Okay? According to KCL, that is, I mentioned already. Yeah. If you increase the V out, then the AC current here will increase. And according to KCL, this AC current will flow in that way. Oh, congratulations. What does it mean? This is the so-called positive feedback. If you increase it, again, yeah. If you increase it, the current here will be increased also, right? And I help you to think, to guess. The AC current will also be in this way to make the overall AC even more. Okay? So that is some kind of positive feedback. But anyway, if you apply, so the major difference between positive and negative feedback is if you increase something, yeah, for positive feedback, the parameter will be further increased. But for negative feedback, the parameter will be pushed back. Okay, that is the mechanism here will reduce the amount by your feedback. That is negative feedback. Okay, if it is used to increase the parameter for you, then it will be positive. Anyway, if you would like to do such kind of analysis, you can apply small signal model, and finally you will see, hey, why you can get such kind of positive feedback? Because it is negative impedance. I told you already. So after some kind of derivation, you can see this. GO2, GO4, and GO3, bingo. They are more likely to be matched to each other. Okay? Yeah. So according to the gain, you can make this become negative to cancel the others. Yeah, supposed to be. But again, this is also in theory. How about in practice? Sadly enough, Q3 and Q2, they are of the same type. I mean PMOS. Oh yeah, they can be matched. All right. But how about Q1? Sorry for that. Impossible. Okay? Because Q1 is NMOS. You cannot match the same GO of NMOS to PMOS. No. Sorry for that. Again, the doping for NMOS and PMOS are not at the same time. So they cannot be matched. Yeah. And this is the reason why for Professor Geiger, he thought about another way is to tune this, okay, to make the gain tunable. Then after fabrication, if there's anything going wrong, you can tune the gain to make this one as close to 0 as possible to enhance the gain. Yeah. So this is the overall block diagram of the prototype they designed with such kind of negative conductance amplifier. So it is not so important. It is basic amplifier. The second stage, I think you learned it already. Yeah. So this fully differential one actually, yeah, because it has two outputs, right? Yeah. Anyway, it is adopt this idea to tune A. All right. To make this to that. Anyway, So let's go for the result. There's some kind of real implementation with AMI in Austria, I guess. Okay, yeah. AMI 0.5 micron CMOS process. Okay, that is some kind of diphoto. And this is the DC gain measurement. Don't be fooled. You can see for chapter 3, for channel 3, the scale is much smaller than the others. Then for all the others, they are for each grid, it means 50 millivolts. Yeah. Anyway, you can see for such kind of very small signal, after amplification, you can see you get a very beautiful square wave. It means what? The gain is really, really high. Okay? Anyway, that is the same. So I would like to show you this. Because you cannot match GO of NMOS to PMOS, you still need some kind of fine tune. All right? They have no idea how much the gain need to be. But anyway, after fine tune, you can see the control voltage. Okay? You can change the control voltage to change the gain. Anyway, you can see the major DC gain look like this. So what is the highest peak? Wow, more than 80, almost 85. Well, it's really amazing. Okay, for 80 dB in linear scale, it means 10,000, right? Wow, an op-amp, a single op-amp can offer you more than 10,000 in gain. That is really fantastic. Okay, so again, without positive feedback, you cannot make it. But anyway, you need to be very careful. Yeah, the stability problem. I mean, for stand-alone op-amp, it is more likely to oscillate. Okay, so you need to put it into some kind of negative feedback control for your application. And this is the measured gain versus output swing. You can see the higher gain, yeah, in this direction. The higher gain means what? The smaller output swing. Okay, so usually for our patched design, for each single op-amp, I mean two-stage or anyway, okay, usually you can achieve around 1,000. 1,000 means 60 dB, right? So where, this is 60 dB, right? So the output swing is more than 800 millivolts. It's quite large compared to the previous design, the old design. But they are curious about the stability of the control voltage. So they try to measure, this is about room temperature. Room temperature usually means 25 degrees, but I have no idea. Maybe in North America, they are colder. The weather there is colder. So sometimes the definition in North America is different from the others. They sometimes apply 20 degrees for room temperature. But anyway, not much indifference. Anyway, they also measure 0 degrees. And then you can see, again, in this area, you can get the maximum gain. So it means no much indifference, even according to temperature variation. All right? So what is the conclusion? If possible, after fabrication, yeah, you can have some kind of automatic gain control or automatic tuning to fix the control voltage around this area. Then you can get very high gain through the help again with positive feedback instead of negative feedback. And this is some kind of frequency response, yeah, for you to refer. So totally, you can see this is the performance summary. Okay, the highest DC gain can be achieved as 85 dB. Yeah, for DC gain more than 60 dB, the peak-to-peak output swing actually is almost 900 millivolts. Blah blah blah. And for the others, actually, they are about the same as the traditional op-amp. Nothing to mention. Okay. Yeah. So, in brief, you can achieve very large DC gains through the help of positive, positive feedback. But anyway, you need some kind of calibration algorithm to stabilize your control voltage. Anyway, yeah. And you can see such kind of structure. I mean, if you apply positive feedback, then such kind of structure can be applied to low voltage, but you can still achieve high gain and high speed. But anyway, the major drawback is nonlinearity. Wow. So if you go back here, you can see, wow, right? Very high gain here, but the gain will decrease very much beyond the region here, okay? But I think I mentioned already, only if the gain is large enough, we don't need to care about the others. You can sacrifice the gain, high enough gain, yeah, to enhance all the other parameters, including linearity. So even though you need to face such kind of nonlinearity for the op-amp itself, but only if the gain of the op-amp is high enough, you can sacrifice it to enhance even the nonlinearity, even the linearity for the overall circuit, okay, not the op-amp itself. And then for the second test chip, I think, oh, it is even better. It is the so-called, it modified a little bit of the telescopic cascade op-amp with positive feedback. That's it. Okay? Yeah. And to achieve even better performance without any kind of tuning. Okay, you can see this. Yeah. What is the original telescopic cascade op-amp? Yeah. Not this. Okay? Yeah. If you remove the cross connection, then you apply some kind of fixed bias here. That is the original one. That's it. It means what? For the circuit itself, it's almost the same as the previous one. But how can you achieve such kind of positive feedback? Again, some kind of cross connection. That's it. Okay? So, cross means yes. Okay, yes means no. Okay, anyway, with the help of such kind of cross connection, you again achieve some kind of negative impedance for positive feedback. Oh, that is really interesting, right? Positive impedance can only be used for negative feedback. If you would like to get positive feedback, then you need to apply negative impedance. And the most convenient way for you to achieve negative impedance is by such kind of cross connection. Yeah, anyway. After analysis, some kind of hard working. But Professor Geiger's students help you to do the hard work already. All right, the dirty job. So anyway, you can see one negative term here, right? So you can tune, during your design, you can tune this to compensate for all the others. Yeah, anyhow. Yeah, so finally, for rough estimation, you can achieve the gain of this order. Yeah, the third order of this. Okay, it's quite fantastic. This is also the bonus for your op-amp lab for next week. If possible, after you design the second homework, try to think. Yeah, to apply similar cross-section for your open design, then hopefully you can get some kind of positive feedback. Oh. Yeah, anyway. If you think the first stage, the gain of the first stage is still not good enough, then you can apply the second stage. Yeah. And what is the second stage? The high gain stage. Actually, again, it is common. It is some kind of common source configuration. Then one more order according to this. So we can see the power of positive feedback. Yeah. Even only for the first stage, you get third order. You get 3 order to enhance the gain. So the second stage only provide an extra order to make it full. That's it. All right. Anyhow, let's go for it. So it means what? Again, for traditional one, they don't have this. That is the only difference in structure. Okay? With this cross-sectional or not. Right? That is the only difference. For all the others, they are about the same. I cannot say exactly the same. Yeah. The major challenge for such kind of negative impedance or cross connection actually it is hard to stabilize the Q point. During design, usually you will face some transistor is pushed into trial region or cut off. So the major challenge is to make everybody operating in saturation region. That's it. Okay? Yeah. Easy to say, easy to talk, but really hard to implement. Okay? Anyway, the concept is quite easy from this connection to that. To get some kind of negative impedance or positive feedback, blah, blah, blah. Let's go for the result. So Professor Geiger and his students are not only talking, they are also doing. Okay? They help us to design this. So why there are 2 curves? Simply because this is the typical one, and that is the positive feedback one. Okay? With positive feedback and without. Oh, you can see, they look almost the same. The only difference is the gain increased by almost 20 dB. Okay, 20 dB means what? 10 times larger, right? They don't sacrifice anything. With the same structure, it means even with the same supply voltage, they can achieve 1 order higher in gain. Wow. And let's go for phase margin. Again, both curves look about the same. Okay? That's it. So, allow me to highlight the final result. The same telescopic amplifier, but with positive or without positive. That is traditional one. Okay? You can see the only difference is the gain is increased from 65 all the way to 81, almost 1 order larger in gain. But for the others, the unity gain frequency, the load capacitance, the phase margin, total current, supply voltage, almost the same. I cannot say exactly the same, but almost the same. This is the major difference. Even for the power, exactly the same, almost the same. Okay? Wow! To enhance the DC gain, you don't need to increase the power. Wow, that is really fantastic. Usually in the past, if you would like to enhance the gain, usually you need to increase the power, right? But through the help of positive feedback, you can make it. And again, positive feedback is one of the technique you dare not apply in the past. Okay? Because you were afraid, oh, after applying such kind of positive feedback, the op-amp will become unstable. So what? So what? Only if the overall circuit is stable. No worries. Yeah. So that is some kind of highlight of the test chip. Yeah. But I told you already in last week, they get help from TI, so they try to dig out the old amplifier with the new one, and the chip area is reduced by 67%. Yeah, the new one only occupies 1/3 of the area. Okay, hey, don't be fooled again. The op-amp design from TI, I mean the past, was not the same. Okay, not what I mentioned here. They said, hey, look, you told us they are of the same structure. The only difference is this and that, right? No. I mean, the new one applied this structure, and how about the old one? Who knows? Professor Geiger didn't need to know, right? He only got the chip from TI, and his students, I mean the layout, from TI. So his students just dug out, just remove the old op-amp. Who knows what kind of structure they apply? Don't care. Just put their new layout for the new design here. Okay, and after test, even the test engineers thought the new one is the original. Okay, the one with a little bit better performance. Actually, to be honest, after measurement, especially for such kind of ADC, the most important parameter is INL, and the second is DNL. Okay, the engineers thought about the same, but which one is the old one? They choose a little bit better, the chip with a little bit better performance, but after the seal, wow, that is a new one. Okay, so you can see, even they can reduce the area of such kind of op-amp by 67%. They still achieve exactly the same performance, or a little bit better performance. I'm talking about for the overall ADC. If you compare apple to apple, I mean the performance of the new op-amp to the old op-amp. I promise you, the new one is much better than the older one. Okay? That is a really, really fantastic proof. For what? Be brave. Sail your boat to the end of the world. There isn't any end of the world. Yeah, you will find the new territory. It means America. You will be the king of America. Yeah, you can live happily since after. Blah blah blah. Yeah, that is a very inspiring story for you. Okay, again, don't fully believe in everything you learned from the papers, from the textbooks, or even from my teaching. You need to be always be curious. Oh, is it true? After thinking, right? After complete thinking, enough thinking, you say, oh, this is correct. Then such kind of idea will be embedded into your brain. Such kind of good idea will live happily with you since after. If you believe in everything, so you don't think, right? Everything I teach you, everything you read from the papers, from the books, you just read that, oh, that is true. Okay, we don't need to think. I promise you. Yeah. During reading, you get it. After reading, you miss it. Okay? And also some kind of, I cannot say wrong idea, but at least not so correct idea, yeah, will stay in your brain to hurt your own futures. So my recommendation is think. To read and then think, right? Don't do anything silly, just in the past. To read and believe, no. To read and think, okay? All right, and what else I can help? I think I finished. Oh, yeah. See, that is an even crazy idea, right? If you would like to enhance further the gain, you can have double cross connections to apply more negative impedance to get much high positive feedback. Wow, you can achieve much higher gain. But what is the cost? What is the price you need to pay? Even harder to stabilize the overall circuit. Again, even harder to make everybody operating in saturation region, to be honest. Okay, so nothing is free. You need to pay for your hard work. Yeah. So forget about the others. The second chip actually is not so fantastic. So, for the second chip from Professor Geiger's group, they would like to develop the so-called some kind of calibration algorithm. After fabrication, they would like the humankind don't need to be involved. They would like to develop some kind of program, to test the chip, then fine tune. Yeah, but to be honest, that is too complicated and impractical. So forget about it. Yeah. Enough is enough. Okay? And finally, I think I told you already how to do such kind of rail-to-rail open design. Yeah. To be honest, usually for output, it is closer to rail operation than the input. Because you have the input differential pair. I told you already. This is for MOS. Yeah. Too low means it doesn't work. All right? Yeah, above some kind of threshold, it is functional. That is the usual case in the past. All right. So how to make even the input close to rail? How about P-type? It doesn't work here, but it works there, right? So both operate in parallel. Congratulations. And this is original N-type, differential pair, and that is P-type differential pair. They are connected in parallel. Okay, that's it. Yeah, anyhow. Okay. For the rest, actually, there are some kind of different common mode feedback circuits. If you are interested, study it by yourself. We don't have enough time. To the end of the semester, I cannot teach you everything. Sorry for that, because time is limited. But I'm still really proud of myself. I wouldn't like to teach you everything, but maybe you only get 10 or 20%. You only understand a few tenths of percent. No. I hope I can teach you maybe 70 or 80%, and you get some kind of full understanding about what the concept I would like to teach you. That is what I hope I can help everybody in the class. Okay, this is the end of the open design with 300 pages. But maybe I teach again, even for the chapter, maybe 70% or even 60%. But I hope you get what I teach you, okay? Then we go for the next chapter. From the beginning, I refresh your mind about semiconductor physics. Yeah, and then we go for the simplest device. It is diode. And then MOSFETs, right? Then we can, no. After that, after devices, we go for the simplest circuit. That is the current source. After you can design good enough current source, then we go for the most important building block for analog IC design, op-amp, right? But after op-amp, what you can do? Oh, hopefully, we can focus on the most important IP for analog IC design. I mean data converters. It includes majorly ADC and TDC, but not limited. Yeah, data converters means you convert A to B, okay? That is any kind of conversion. So not only for ADC, yeah, what is ADC? The input is usually voltage, but sometimes current. Okay, to what? Digital. This is input, that is output. You convert the analog voltage, analog current, I mean usually, to digital. That is the definition for ADC. Okay? So, on the contrary, what is DAC? DAC, digital to analog converter. What is the input? Digital. Digital value. To what? To analog voltage or current. Okay? So, are there only two data converters? No. I told you already. Anything you convert from A to B, they can be called data converters. So, for the others, for example, we have TDC. The input is time. Okay? The output is digital code. That is the so-called TDC. Also, a very important IP, especially for example, laser ranger, right? Laser 测距仪. You shoot your laser on the target after reflection. Yeah, the longer distance, the longer time of flight. Time of flight. 飞行时间. That's it. Right now, it is really important. For what? For autonomous car control. 自驾. Or unmanned driving. Unmanned. No man. Okay, without the help of man, you can drive by yourself. Not only for cars, for drones, yeah, or even for submarine, yeah, for any kind of autonomous driving system, control system, yeah. But how can the car decide whether or not in front of it there is some kind, the other car or a human kind, blah blah blah. Okay, they need the help of LiDAR. LiDAR means use laser to scan the environment. Okay, then reconstruct the 3D map. Yeah, something very like that. Okay, but with steps. Okay, so if I scan the class, I will see Ahmad there, John there. Yeah, but roughly, yeah, not so accurate. Maybe for depth or distance, I guess 10. I mean the accuracy may be around 10 centimeters should be good enough. Okay, because usually for driving we don't get so close to humankind or to the other cars. That is too dangerous, right? I guess you don't need to get such kind of centimeter for resolution. It doesn't need. Yeah, but anyway, the major challenge is to scan such kind of three-dimensional environment real time, in a real time way. Okay, real time means real hard, right? It means you need to scan again and again. So you can see for such kind of unmanned car, on the top of the car, there's something, yeah, rotating, just like radar. Okay, so what is the difference from LiDAR and radar? radar with wireless wave, RF radio waves, right? That is for that is for radar. Just like what you can see on the ship or the airplane, okay? That is for radar. But for cars, we need LiDAR, yeah, to get better resolution. Why? Because C equals F lambda, right? That is the light speed. Never mind, you use laser or RF wave, I don't care, right? But for frequency, LiDAR means light. The frequency is much higher than radio frequency, right? So it means what? The same light speed in the air, but LiDAR using laser. Laser gets much higher frequency than RF wave, so the lambda is much smaller. And lambda is strongly correlated to your distance resolution. That's it. And this is the reason why for airplane, for warship, they use radar. Because for the other airplane, tanks, yeah, or ships, they are really large. Okay? And they don't fight each other with such kind of very close distance. Usually, kilometers away, they fire a missile to kill you. That's it. Yeah, to play safe. Okay? So the radar system doesn't need such kind of 10 centimeter or even meter in resolution. Too much. Maybe 10 meters or 100 meters, I think, good enough. Okay. Anyway, that is the major difference. Again, I'm talking about data converters, not only ADC, not only DAC, but also TDC and all the others. Yeah, we have TDC, we also have DTC. Digital to time converter for what? For IC testing. Okay, to test the timing of your chip, we need a lot of DTC. Yeah, or sometimes we call it arbitrary waveform generator. Yeah, 任意波形产生器, AWG or something. Okay. Anyway, for such kind of very luxury equipment, it converts digital input. As an engineer, you can set up the whole system to generate any kind of process. Okay. Yeah, the width, the duration of the period. Okay, of the frequency. Yeah. Anyway, or you can set to the difference between two per signal. Blah blah blah. Anyway, anyhow, it is really expensive. All right. Humankind apply such kind of equipment almost for every day to test all the chips fabricated from TSMC, UMC. So I would like to tell you, there are many kinds of data converters. But before I teach you how to design them, I hope you can get full understanding about the logic thinking, the most important ideas about such kind of data converters. Especially, what is good data converters? What is the major parameters you need to know? Okay, what is operation principle? So before I teach you anything about ADC or DAC, we will have a brief introduction for any kind of data converters, especially what is INL, what is DNL, and what is the effective number of bits. There are many kind of important parameters, or we so-called terminologies. Okay, 有一大堆名词，有一大堆定义。Anyway, before you're learning, you had better get full understanding. I guess for most of you, you won't design any kind of ADC or DAC. Okay, but you still need to know what is the major concept. Okay, just like cars. I don't think you will design your own cars. No, but you need to know how to buy good cars, right? So that is what I hope. Maybe you don't need to design, but you need to know. For example, if you are some kind of manager, Yeah, for your team. You don't need to design the ADC or the DAC, right? But you need to know how good the chips designed by your employees, okay? Or you need to discuss with the salesman from the other companies. You need to cut the price. All right, I will tell you how to cut the price to the end of the introduction chapter. Okay, so it is the beautiful ending for OPAM. Then we have a break. After that, I will introduce the major concept for data convergence to you. Thank you.